Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss isotope effect on BCS theory. Let's begin. First, isotope effect. Isotope effect is observed by two scientists. One name was Maxwell and another name Reynolds. As you know, superconductivity is the phenomenon at which at a particular temperature, or we can say that is the critical temperature, if a specimen suddenly drops its resistance to 0 is known as superconductivity, and the specimens which show that phenomenon is known as superconductors. Means critical temperature is responsible to show either that one is superconductor or not. Further observations are continued, and two scientists Maxwell and Reynolds observed that critical temperature relates to that of isotopic mass of that particular specimen. What was their observation? According to their observation, the critical temperature of superconductors decreases with increasing isotopic mass. Isotopic mass, let capital M. So mathematically we can write it, the critical temperature T of C is inversely proportional to that of isotopic mass 1 divided by under root of capital M. Therefore, critical temperature Tc under root of isotopic mass, the product of these two quantity is a constant. That was the observation by these two scientists. If we plot a graph in between critical temperature along y axis and isotopic mass along x axis, means its reciprocal, its inverse under root of m 1 by under root of m along x axis, then we obtain that kind of graph. That graph shows if critical temperature increases of a superconductors, that is the decrease in isotopic mass. Therefore, we conclude the variation of critical temperature of an element with its isotopic mass is known as isotopic effect. The variation of critical temperature of an element with its isotopic mass is known as isotopic effect. And that isotopic effect first of all observed by these two scientists Maxwell and Reynolds, and he observed that isotopic effect in case of mercury. Example, in mercury the average isotopic mass varies from 199.5 to 203.4 AMU atomic mass unit, and the value of critical temperature changes from 4.185 to 4.146 Kelvin. That be the isotopic mass, that be the critical temperature. These two are varies with each other, and that kind of effect is known as isotopic effect. What was isotopic effect? The product of critical temperature to that of atomic mass unit under root of atomic mass unit is a constant. This is isotopic effect. Now we have to discuss BCS theory of superconductivity. We know what is the phenomenon of superconductivity, and the materials which obey that phenomenon are under the category of superconductors. That superconductivity phenomenon can be verified, or we can easily understood by BCS theory. Before BCS theory, there are so many theory in order to explain the phenomenon of superconductivity, like London's theory and so on. But there are a few drawbacks. In order to avoid that drawbacks, a well known, or we can say a famous theory was in front of us, that was BCS theory of superconductivity. So what is BCS theory? This is the quantum theory of superconductivity, and that was given by three scientists, Barden, Cooper and Schrieffer, in the year of 1957. The first letter of the scientist's name as Barden B, Cooper C and Schrieffer S. Combining the first letters of these three scientists, and their proposed theory was named as BCS theory, which is known as BCS theory. Let me explain what was BCS theory. This theory can be explained by using two important terms. One is electron-phonon interaction and another one is Cooper pairs. If we understand these two concepts, then we can easily understood what was BCS theory. That was a well explained theory. By using that BCS theory, we can easily explain the phenomenon of superconductivity, and by that theory, these three scientists have have the Nobel Prize winner. Let me explain that BCS theory. What was electron-phonon interaction? In lattice vibrations play an important role in the theory of superconductivity. What was lattice vibration? For lattice vibration, let me take a superconductor as lattice points. When an electron approaches an ion in that of lattice, both interact electrostatically. Let we have to join these are the positive ions on that of lattice points, and these are vibrate on their mean positions. So, lattice vibrations play an important role in the theory of superconductivity. When an electron approaches an ion in that of lattice, both interact electrostatically. If an electron will be there, then these positive ions are interacted with that of electrons. This positive ion attracted towards that of electron. Thus, momentum is imparted to ions, which causes them to move together due to elastic behavior of lattice. How it reacts to that of electron? These are the positive ions. Inside that positive ions, that with the electron. So, that point is distracted to this point, that also attracted to this, that is this, that is that. Now, that lattice point are distorted. Okay. When an electron approaches an ion in that of lattice, both interact electrostatically, ion with that of electron. Thus, momentum is imparted to ions, which causes them to move together due to elastic behavior of lattice, and this slight movement together increases the positive charge density in that of region. Now, the positive charge density increases with that region. In that region, the positive ion density increases. Okay. And which is known as phonons. That region we call it as phonon, where positive ion density is more within that region. that region where positive ion density increases, and the region of increased positive charge density propagates a wave which carries a momentum through that of lattice. Now it propagates a wave which carries a momentum through that of lattice. Again, at this stage, if another electron passes by the moving region of increased positive charge density, so what happened? Let me explain it. Here the positive ions here is the electron, and now these are the distorted position. The distorted position, and that region the highly dense positive charge which is known as phonon. If another electron passes by moving region of increased positive charge density, it will experience an attractive Coulomb interaction. Another electron, there will be another electron. Here is positively dense charge, that one is electron. So positively dense charge with electron, they are attracted with each other, but again inside that of positively dense charge there will be an electron. So electron repelled with each other. So what will be the net electrostatic force? That is explained here. If another electron passes by the moving region of increased positive charge density, it will experience an attractive Coulomb interaction and hence can absorb all the momentum the moving region carries. In other words, we can say the second electron can absorb the phonon, thereby absorbing the momentum supplied by that of first electron. Thus, the electrons have exchanged momentum through an interaction involving phonon as intermediary. In this way, interaction between two electrons take place. This is an attractive interaction because at each step electron participate in an attractive way. Here is the positively dense charge, that one is the negative. These two are attracted with each other, attractive way. This interaction between two electrons by that of phonon, that is the phonon, positively dense charge, that interaction between two electrons by that of phonon exceeds the Coulomb repulsion. Electron repelled with each other, that is Coulombic repulsion, and phonon with that of electron, that is attraction. So that attractive force is much more as comparison to that of repulsive force. The interaction between two electrons by phonon exceeds the Coulomb repulsion, and the pair of these two electrons is known as Cooper pairs. These two pairs, as electron, there will be an electron, here is an electron, which one is positively dense charge, which is known as phonon. They are interacted with each other, and that pair is known as Cooper pair. And electron pair is known as Cooper pair. First we show what is electron-phonon interaction. Here is the electron, how the lattice points are distorted due to this scenario. That region is positively dense charge, which is known as phonon. And now if another electron will be there, these two are interacted by that of phonon, and that attractive force is much more as comparison to that of repulsive force, and the electron-electron pair is known as Cooper pair. By that way ED proceeds throughout that of lattice. In all these discussions, as we discussed electron-phonon interaction and Cooper pairs, we can explain it by using quantum mechanical terms. How? First situation, that is electron just like a wave, the wave vector, the k, when incident it releases a phonon having q vector is a phonon, and that electron scattered with wave vector k minus q vector. Again another electron interact with that of phonon, let that be the wave vector k dash. Therefore the scattered electron having the wave vector k dash plus q. Overall, what are the processes are involved in that of BCS theory, we can explain by using the quantum mechanical terms. Okay, here is the BCS theory on superconductivity, and we explain that BCS theory by using two important terms. One is electron-phonon interaction, another one is Cooper pairs. So what was electron pair interaction? We show it by diagrams. And what was Cooper pairs? We explain it through that of diagrams. And all the processes like electron-phonon interaction and Cooper pairs we show in terms of quantum mechanical way. So here with the help of this video lecture you understand the concept of isotope effect, graphical view, example of mercury, BCS theory in superconductivity, so with this useful and informative notes, let me wind up this session. Thank you.